Good evening, everyone. I suggest we today continue playing with arrows and considering different mechanisms of the chemical reactions. Many of these reactions we will meet in the future when we will consider some sort of biochemical pathways, so it's really nice to know some sort of whatever is happening there behind the curtains, and so we can at least imagine some sort of chemical or physical processes that are underlying certain biological phenomena. And we have already considered some sort of substitutions reactions and mechanisms like SN1 and SN2. And today it will be nice to consider some more types of reactions, especially the nucleophilic addition and elimination reactions. So there are three types of elimination reactions that I will show you, and well, we will get to that. Okay, so nucleophilic addition. You might guess that addition means that we are adding something to something. So we had two molecules, and we will get, at the end of the day, we will get just one molecule out of that two molecules. A really let's say useful example that we will see here and there is the nucleophilic addition to aldehyde or ketone. So let's focus on that. In this case, the nucleophile, so that's why it's nucleophilic addition. If that were electrophile, that would be electrophilic addition. So, but this is a nucleophile, so we have a nucleophilic addition. It approaches the molecule. So here you see the angle, something around 75 degrees to the plane of the double bond. So you might guess we have here double bond O, so this means we have one sigma bond here and we have pi bonds here. So I can draw these sort of orbitals. They will overlap and we will get these sort of clouds of the electron density, and that will be our pi bond. So this bond makes this molecule planar, and nucleophile is approaching approximately at 75 degrees. Now what happens? Nucleophile has some electrons, so for example this may be some non-bonding electron pair or something like that. These electrons this electron pair from the nucleophile, it adds to the electrophilic carbon of the carbonyl group, pushing the electron pair from the CO bond onto the oxygen. So it's bringing its electrons, they have negative charge, and they are pushing like these electrons from the pi bond onto the oxygen. Oxygen is pretty electronegative, so it is happy to get these electrons for himself. But now what changes? We are creating a new bond to the carbon atom. And now this carbon atom has no double bonds. So you should remember that this changes the hybridization, and we have this carbon atom rehybridized from sp2 to sp3. So here it is. So we have some sort of tetrahedral intermediate. So it's no more planar, it's tetrahedral. And this is some sort of alkoxide ion that is some sort of intermediate for this reaction. Then what happens? This alkoxide ion, it carries some negative charge on the oxygen, and it will be happy to get some proton for himself. And the protonation of this alkoxide ion, of this intermediate, gives the neutral alcohol addition product. So here we had some aldehyde or ketone, and here we ended up with some sort of alcohol and this nucleophile attached to the carbon atom. Good. Here is one more example. it showed that we can use as a catalyst either acid or base. So acid or base catalysts, they increase the rate of equilibration of hemiacetals with their aldehyde and alcohol parents. So here you see the hemiacetal. So here are these oxygen atoms that define, let's say, that justify its name. And here you see that we had an aldehyde. This aldehyde was in acidic condition, and under the acidic conditions, this oxygen can be protonated. So we have this oxygen protonated. Now it acquires some positive charge, so it would really like to get some electron. So when a different molecule approaches, it may attack the carbon atom, and the electron density is pushed onto the oxygen, and it happily accepts these electrons. So at the end of the day, what do we have? So the thing transforms into the OH, and the thing attaches to the carbon atom. So here it is. Now, after this attachment, we have our carbon atom rehybridized. So this carbon atom has now rehybridized, so this is a tetrahedral intermediate, and now one of the hydrogens may leave. So electron pair goes here, goes onto the oxygen becomes neutral, we get some hemiacetal, and this sort of proton leaves. What it means that the proton we had at the beginning of the reaction that was protonating our oxygen is regenerated at this step. So we have plus H plus. So that's why it is a catalyst. So it is not taking part in the reaction like some sort of reactant, but it is just some sort of catalyst. So it helps the reaction to proceed and to equilibrate these two chemicals. Another example is base catalyzed hemiacetal formation. So once again we have this sort of hemiacetal. You might see that this is the same hemiacetal as this one, so it's just a little bit drawn differently here, but that doesn't mean anything. And here we have the action of the base. So what is actually making the base here? So we had reaction between alcohol and and aldehyde, and here we have base abstracting a proton from the alcohol. We get O minus. That's pretty potent nucleophile, so it really would like to attack anything that has some positive charge. And we know that this carbon atom, it has some electron density of its electrons are shifted towards the oxygen atom, that is electronegative. And once again we have attack of the nucleophile onto this carbon atom. Electrons go onto the oxygen, and here is what we get. So one oxygen acquires negative charge, and this part is attached to the carbon atom. So that's what we get. Now these negatively charged oxygen may abstract some hydrogen atom to become basically neutral. And if we had some conjugated acid with our base, so this is our base, the whole construction is conjugated acid, we are basically regenerating our base, because here we have abstracted a proton, so we have transformed our base into the conjugated acid, and here we are regenerating our base. So once again, base is acting only as some sort of catalyst. Here is the same reaction, just drawn a little bit differently. And what's interesting, we have some sort of demo. Let's check it out. So here is the demo of the reactions as they go. let's try running this demo if we are able. So here we have it. So now we are protonating. In this case, we don't have aldehyde, we have some sort of ester, and here is our ester, and we are protonating the oxygen atom. Let's do that. So here it is protonated. It acquired some positive charge. Now it will try to take the electron from the pi bond for himself. At the same time, this thing is attacked with the water molecule. So here we have this sort of reaction. Let's check it out what happens. So here is a nucleophilic attack. So let's check it out. So electrons moved here, oxygen is neutral, water molecule is attached, but now it acquired some positive charge because electrons were used for creation of these bonds, so they are not now exclusively, they don't exclusively belong to the oxygen atom, but they are shared with this carbon atom. And now what we get, we will want to lose one of the protons and transform our oxygen to the neutral form. So let's check it out. So proton leaves, and we have the sort of addition product. So here it is. This is a hemiacetal, and we can go basically another way. So this is acid catalyzed ester hydrolysis. So here it is. All these reactions are in a sort of equilibrium. So depending on what products you remove from the reaction space and other things, you might get one more or less of these products. So the only way to control the reaction is by altering the concentration of the reagents to drive the reaction the way you want. For example, the excess of water will force the hydrolysis of the ester, whereas an excess of ester or removal of water forces the reverse reaction, that is the formation of the ester. So depending on what happens here. And we can go even further. So here we have so here's what we have our ester. We still can protonate something, so here we are protonating our oxygen atom. So here it is protonated, it acquired some positive charge. Now what may happen, we have some non-bonding electron pairs on these oxygen atom. One of them can be used to reform the double bond, while these electrons can go onto these oxygen, and basically here's what happened. Oh, sorry, not this. This image. Okay, it's in a different direction, but anyway, you get it. So we can get from two molecules, we can get one, or from one molecule we can get two. So here it is. Yeah, that's the right direction. So we have reformed our double bond, and now we have two different molecules. So here is some sort of alcohol, so OH group, and here we have our double bond oxygen and and OH group. Now what do we have next? Now we can this hydrogen atom can leave, and we will reform once again the neutral oxygen atom. Here we go. So here's here's what we have, and this is some sort of basically some sort of acid. So this is acetic acid. Good. Okay. Um, Basically, these sort of reactions, so like nucleophilic addition, it is used in biochemistry and used during different syntheses of different drugs. For example, some and you may see that in different mechanisms that are involved with how different drugs work. For example, here is some sort of anti-cancer drug, or even two anti-cancer drugs like heleniline and vernolipine, and they work by conjugate addition to thiols. So drugs to combat cancer, they act on a range of biochemical pathways, but most commonly on processes that cancerous cells need to use to proliferate rapidly. So they rapidly proliferate, and we don't want that. So many others, well, most cells in our body, they don't proliferate either at all or do that really, really slowly, where there are only small exceptions to that. So basically, we are trying to stop any proliferation that will do some damage to a certain extent, but definitely it's not comparable to the damage that cancer is doing to us. So most drugs will be targeting something like that. And one of the classes of the proteins that we would like to attack and stop and prevent from working, that's the DNA polymerases. And this is the enzyme that is needed to make a copy of the DNA to be provided to every new cell. And these two drugs, if you look at their structure, you should be able to spot two alpha beta unsaturated carbonyl groups in each. And biochemistry, of the process, it's a sort of conjugate addition reaction between a thiol, so SH group of the one of the enzyme's cysteine residues, and the unsaturated carbonyl groups. So the reaction is irreversible, so it shuts down completely the function of the enzyme. And here is one of the examples. So here you see the attack of the non-bonding electron pair of the sulfur atom. It attacks here, basically creating a new bond. So here you see this new bond created. Well, maybe the best choice of color. So here's our new bond. While these double bonds is basically destroyed, so these electrons are moving up here, creating double bond here, and once again these electrons are pushed onto the oxygen. Oxygen is basically electronegative, so it will not be against that getting a few extra electrons. So here we have oxygen with the minus charge. And basically then we can lose this proton, restore the charge of this sulfur atom, and then restore the double bond of these oxygen atom. So that's basically the reaction we have. Okay, that's good for nucleophilic addition. Let's consider a different type of reactions. These are pretty interesting reactions. These are elimination reactions. As their name suggests, we should expect that something falls off of the molecule. So we had a molecule, and some part of this molecule should go away. There are many kinds of elimination reactions. What we are interested in now That's the elimination that happens when the nucleophile attacks hydrogen instead of the carbon atom. And we will consider three types of these reactions, like E1, E2, E1CB, and do that in some more or less details. As in case of the substitution reactions, when we had SN1, SN2 mechanisms, the E1 and E2 mechanism names are connected basically to the rate of the reactions. So if we have, so E comes from the elimination, that's pretty reasonable, and numbers 1 and 2, they define something like rate of the rate determining step. So if we have this is the example of the E2 reaction, we have two molecules interacting, so we have some some strong base that is abstracting a proton. Here you see how electrons flow, and this is the leaving group, so it goes away. So here we have eliminated bromine from these well, from these molecules. And this reaction has the second order, so its rate depends on the concentration of the third butyl bromine and the and OH groups. In contrast, we can have E1 elimination. So here is third butanol. So here you see that, well, pretty similar to what we had here, but we have only OH group, not bromine. And in acidic conditions, so we may have some acidic conditions. Let's say we have some sulfuric acid in the flask. So we have some protons. These protons, they may protonate oxygen. These leads to the very nice leaving group like water. So water is good leaving group, and here we see a very slow step of the leaving group going away. So this is a first order step, because we have only these sort of molecules involved, nothing more. So here we had two molecules involved, here is just one. But in any case, leaving group is going away. We get a carbocation. So here it is, the carbon atom with plus charge, that's carbocation. And now this carbocation can undergo some sort of restructuring. For example, this is the conjugated base to the sulfuric acid. Conjugated base, well, may like to get some protons, so it may abstract proton from this molecule. We have electrons that flow here, basically creating a double bond, and at the end of the day we get the isobutene or 2-methylpropene. So that's what we get. What's interesting here, you might notice that this reaction is pretty similar to the mechanism of the nucleophilic substitution. In similar conditions, we had the same protonation and leaving of the leaving group that leads to carbocation intermediate. And once again, we get, for example, we have here bromine that attacks this sort of carbocation, and we get third butyl bromine instead of isobutene. So you might ask, how do we differentiate these cases? So should we expect the substitution reaction or the elimination reaction? And here is some sort of guide how to understand what should we look for. So how the nucleophile, so basically the nucleophile will define are we looking at the elimination or the substitution reaction. That's because everything else is pretty similar. So what do we have here? So there are basically three effects. Nucleophiles that are strong bases, they favor elimination over substitution. Nucleophiles or bases that are bulky, they favor elimination over substitution. And high temperatures favor elimination over substitution. Let's start with the third point. So here is the formula for Gibbs free energy. The interesting part is this one. Temperature times change in the entropy. When you have elimination, that means that you had one molecule and this molecule was transformed or split into two. This means that entropy grows up, so you get some higher entropy. So if the temperature is high enough, so if the temperature is really high, is high enough, this term of the free energy will dominate. So if you have high temperature, the this term, the entropic term, dominates, and it is more and it favors basically elimination over the substitution. Because in case of substitution you get the same number of molecules, in case of elimination you get more of them, and this term brings you brings your free energy more down. Good. So what about other cases? Let's consider some sort of intuitive level. So here we have weak base, and here we have strong base. So what happens if we have weak base? In case of weak base, it doesn't really want to attack whatever we have here, so this molecule. So it will wait until the living group leaves and we get carbocation. Now this carbocation can be attacked with the weak base, because now we have here some positive charge, so it's much more cationic than it was before. And here the attack proceeds, and we have this sort of result. So that's a substitution reaction. What in case of strong base? Strong base does not want to wait until something leaves. It just grabs the proton and abstracts it. So now what happens? If it grabbed the proton, we have right now some sort of restructuring inside the molecule, some electron flows here and there, and the living group leaves. And in this case, you get the elimination reaction. So this was reaction SN1. We waited until the carbocation formed, and then and only then weak base attacked and was attached to it. And another case, we had strong base that immediately abstracted proton and basically initiated the process of restructuring the molecule and leaving group, well, leaving. So here we have it. What else may influence? The size. If we have a small nucleophile, that will favor the substitution. Why? Because it can get to the positively charged carbon atom and try to attach to it, to place its electrons on the LUMO of this carbocation. So in an SN2 substitution, the carbon center is a soft electrophile. It is essentially uncharged, and with leaving groups such as halide, sigma star, or orbital is a relatively low energy LUMO. So substitution is therefore favored by nucleophiles whose homos are best able to interact with this LUMO. In other words, some soft nucleophiles. And in contrast, the CH sigma star is higher in energy, so the atoms are less electronegative, and this makes CH bond a hard electrophilic site. So here, in case of some small electrophile, we can get to this part, we can attach this OH group, and here we have substitution reaction. If the nucleophile is bulky, it just cannot get to this carbon atom due to the steric hindrance, so it attacks a hydrogen atom. Of course, it should be strong enough to get the hydrogen atom, but when it grabs this proton, here we have once more electrons flowing here, and the leaving group is leaving, and we have a double bond formed. So that's what we get. Okay, so suppose we have decided our reaction is the elimination reaction. Now let's check out these three types of elimination reactions and get through them just one by one. So here we have E1 reaction. The CX bond breaks first to give a carbocation intermediate, and followed by base removal of a proton to yield, let's say, an alkene. So here we have our initial molecule, our substrate, leaving group leaves, so here it leaves, we get some carbocation intermediate. So now if any base will abstract this proton, we will have some electron pair to put in here, to put here, and to form a double bond. So here it is, E2 reaction. CH and CX bonds, they break simultaneously. So that's why E2, because we have two molecules interacting. We are not waiting for some carbocation to be formed. So base grabs a proton, we get electrons that can be used to form a double bond. On the other hand, this carbon atom now will have too much electrons, so he just gives away his electrons to the X. And this yields once again an alkene. And E1CB reaction, so CH bond breaks first, gives a carbanion. So if we have really strong base, we can grab this proton. Now these electrons have nowhere to go, so they leave some time on the carbon atom, basically making it electronegative. Now these electrons are trying to create a double bond to a different carbon atom, and this leaving group is trying to leave, and once again we get an alkene. So an elimination reaction, these mechanisms that we have considered, they consist of a formation of a double bond by the removal of two single bonds from adjacent carbons. A leaving group attached to a carbon and a hydrogen attached to an adjacent carbon will usually be the two bonds broken in these types of reactions. So here's once again E1, that's elimination reaction. Here we have a rate determining step, leaving of the leaving group. Here we have carbocation, and here base is abstracting a proton, creating double bond. So here we have rate, it's basically the proportional to the concentration of the alkyl halide, because this is rate determining step. So here is E2 mechanism, and here we have rate of the reaction proportional to the concentrations of base and the alkyl halide, because they should interact so that abstraction of the proton and leaving of the leaving group are simultaneous. Good. What else? There are basically a number of factors that affect whether the elimination goes by E1 or E2 mechanism. So only E2 is affected by the concentration of the base. So once again, in the E1 reaction, we have rate determining step that does not involve base. So if you add it, nothing changes. So only E2 is affected. The rate of an E1 reaction is not even affected by what base is present. So E1 is just as likely with weak as with strong bases, while E2 goes faster with strong bases. Well, that's basically reasonable. Because once again, rate determining step for E1 does not involve any base, so whatever you use, everything's okay. While E2 involves, and you want to have some stronger base to abstract that proton. So here is one example of the diene synthesis by double E2 elimination. Just an example: base abstracts proton. These electrons are used here to form a double bond, and these bromine leaves. The same reaction here, and once again bromine leaves, and we have a double bond. So here's the overall reaction. A bit more details regarding E1 reactions. So the mechanism of E1 reaction, once again, two steps are involved. The first one is the rate limiting. So here you see the spontaneous dissociation of the tertiary alkyl chloride yields an intermediate carbocation in a slow rate limiting step. So this is rate limiting. Now you have base, abstracts proton, and pretty quickly loss of that proton leads to a neutral alkene product. The electron pair from the TH bond goes to form the alkene pi bond. So here we have this double bond formed. The steric factors that disfavor SN1 at hindered centers don't exist for eliminations. Nonetheless, E1 can occur only with substrates that can ionize to give relatively stable carbocations, so tertiary, allylic, or benzylic alkyl halides, for example. Here let's check some different cases. So here we have some tertiary, allylic halides, and so on. The thing is that we want our carbocation to be stable. So the more stable is carbocation, the more happily leaving group leaves. And we remember that this is the first and the most crucial step in the E1 elimination reaction. So we need to stabilize the positive charge that we have. And this stabilization of the positive charge may be performed by some sort of the delocalization of the charges. So you probably should remember that tertiary carbocations are most stable, while the primary are non-stable at all, because here we have many carbon atoms so that we can use for the delocalization of the positive charge. So here is the allylic system. We have a double bond here, and here's basically a pi bond that can be used once again to delocalize the positive charge. So we can use some part of that electron density to stabilize this system. Here is another benzylic system. So we have a ring here, so there is an aromatic system in the ring, and we can use electron density from that ring to stabilize once again this positive charge. So that's what we have. The secondary alkyl halides may eliminate by E1, while primary alkyl halides only ever eliminate by E2. So primary alkyl halides are give non-stable carbocations, so you cannot get E1 elimination. So your leaving group will not leave. So if you will get ever some elimination, you will have the E2 mechanism. And remember that any of these substrates under the appropriate conditions in the presence of strong bases, for example, may undergo E2. So everything shown here, you can make this reaction E2 if you create appropriate conditions. Okay, so here we have substrates that readily eliminate by E1. Here we have substrates that may eliminate by E1. So these all were tertiary tertiary structures, and here we had a lot of places to delocalize our positive charge. Here we have a alpha heterosubstituted atom, so here we have oxygen atom that is basically electronegative. It has some non-bonding electron pairs, and these non-bonding electron pairs we can use them to create some sort of this sort of structure. So once again we are stabilizing our positive charge. This is an example of the secondary structure, and here we have they can eliminate by E1, but once again it's less stable carbocation because you get a secondary structure here, so it's not much opportunity to delocalize the positive charge. What else? Well, I think I said a little bit wrong. Yeah, so here we had a tertiary structure, but these are allylic structures, so, and benzylic structures. Okay, and here is an example of the substrates that never eliminate by E1. This is the primary structure, and you cannot expect this group to leave. And there are some substrates that cannot eliminate by either mechanism. So because there are no appropriately placed hydrogen atoms. So you see that in case of either E1 or E2, we are abstracting some proton, and if you don't have a proton there, you cannot eliminate. So for example, the structure, if you had any hydrogen atom here, that would be possible, but you don't have that just because this carbon atom has used up all 4 bonds that it can form. Here is just a reminder regarding different carbocations, and here you see them in the order from less to more stable, and here you see the electron densities. So here you see some large electron density, some large charge density, and well, it's not good. This is pretty unstable, so you don't have where to delocalize this positive charge. And here you have a lot of places to delocalize the positive charge, and the structure is much more stable. Here is some here is an example of different stabilizing effects, like from donation of the sigma bond electrons. So what do we have here? So here is the methyl cation, very unstable. What can we do here? Here is empty p orbital. Can we look something more? So that's not so interesting. Let's check. Let's check this one. So this is CH. This is this one, tertiary cation. So we have positive charge center and CH3 groups attached to this carbon atom. And if we look here, so here we have some positive charge. We should somehow delocalize this charge. And if you look at the sigma bonds connected to the hydrogen atoms, so here we have some electron density. Part of that electron density can be used, can be delocalized into this p orbital, and this positive charge becomes delocalized. So that's because our sigma bonds, they are almost vertical, so they are almost parallel to this empty p orbital, and they are basically stabilizing these carbocation. And these reds, they are just regular sigma bonds. If we have something else attached to the carbon atom, it still can be used to stabilize what we have here. While in the case of methyl group, you don't have these sigma bonds oriented along the p orbital, and you cannot do that. Well, can I show them or not? For some reason, when I tried to use sigma orbitals, it showed me another cation, but anyway, you can guess. So here we have these empty p orbital, and these are our sigma bonds. Let me use different colors. So here they are, and they are almost they are perpendicular to these empty p orbitals. So you cannot use electron density from here to stabilize the positive charge and to alleviate this sort of situation. Good. What else? Here is one more, I guess, example of the reaction that shows the reaction coordinate and the intermediates. So here we have a rate determining step, so that leaving group leaves, we get to the intermediates. Here we should have some carbocation that is more or less stable, and here we have attack by water that abstracts the hydrogen, and here's what we get. I guess we can look an example here. At the same time, I'd like to check how many slides do I have. Okay, lots of slides, but I guess we can get through that. Here is an example of what we have. Here's our bromine atom, so let's look at that, and it is leaving. So here we have leaving group leaving. Here we have our carbocation that is basically stabilized, its tertiary structure. Here we have water that will abstract one of the hydrogen atoms, so it takes proton away, and here we have our double bond formed. Good. Well, maybe I should stop saying hydrogen atoms, because basically a proton is abstracted, so electrons are still in place and used to form certain bonds, but I guess you get the idea. Good. Just a reminder that E1 reactions can be stereoselective, regioselective, or yield one product. So here is, in this case, only one alkene is possible. So here we have it. These are two regioisomeric alkenes. So here we have two regioisomers, so tri-substituted alkene or di-substituted alkene. So here it is. So you see that this OH group is basically leaving, and you can get either a double bond here or a double bond here, depending on which hydrogen atom you will abstract. And here are two stereoisomeric alkenes that are possible. So once again, you protonate the oxygen, water leaves, and depending on the situation, you can get either E or Z alkene, so cis or trans conformation. So you know that single bonds, they can rotate, and at the moment when these electrons flow, you either catch this part in this conformation, you get trans configuration, or you catch it in this conformation, you get this configuration. Here's one more example of the stereoselective formation of the E-alkene. Pretty interesting that we may have different energies, so different energies of the products, and what's more interesting that this is the first case when we meet so-called kinetic product and thermodynamic product. So in some cases we can get, depending on the situation, we can get one or another. So here is the reaction. So we have a stereoselective formation of the E-alkene. So here is the protonation goes here, so we get some additional proton here. Now this is water, it's a good living group, it leaves, and here we have our carbocation. And these carbocations, so the geometry of the product depends on the conformation of this bond. So how this methyl group will be turned around this single bond will define what we get at the end. So conformations of the intermediate cation with CH and vacant pi orbital aligned parallel. So here you have some higher energy intermediate, and here you have some lower energy intermediate. So that depends on the steric hindrance and so on. So here you have methyl group on the one side with the with the phenol ring, and basically this is a sterically hindered conformation. They don't like to be close to one another, so you get a little bit higher energy, and here you have them on opposite sides, and here you have a little bit lower energy. So in a lower energy transition state, so here it is, here is the intermediate, and this intermediate leads to the E-alkyne formed faster, so they can be stereoselective. This has a little bit higher energy, so here we have some higher energy transition state, and Z-alkene is formed more slowly. But anyway, if you wait long enough, everything is in some sort of equilibrium, so you will get a mixture of that. Here is an example that E1 reactions can be regioselective. So carbocation is stabilized when its empty p orbital can interact with the filled orbitals of parallel CH and CC bonds. The same is true if the pi system of the double bond is stabilized when the empty pi star antibonding orbital can interact with the filled orbitals of parallel CH and CC bonds. And the more CC or CH bonds there are, the more stable is the alkene. So here we have two different products of the elimination. Once again, we are eliminating these OH OH group. So here we have some major and minor products. Here you see that more substituted alkenes are more stable. So here are no CH bonds parallel with the pi star, so they no additional charges to perform stabilization. And here we have some increased substitution. Here you see that this thing is planar, and here you see these hydrogen atoms and these sigma bonds. They are more or less parallel to the pi star, and this is the increasing substitution. So here's once again example. So E1 elimination favors the most substituted alkene product. There are 4 bonds branching from the double bond, and if they contain any molecule apart from hydrogen, they play a part in the degree of the substitution. So the most stable configuration of an alkene is one that is the most substituted. So here you see disubstituted and tetrasubstituted alkene. And these are two possible products of the E1 elimination reaction, and the tetrasubstituted alkene is more likely to be a major product than the disubstituted option. So that's basically what we get. So here is one more example. Once again, we have a protonation, leaving group leaves, and here we have some sort of intermediate. And the product depends on which of these two protons is lost. So whatever we lose, that will define the result of this reaction. So if we lose one of the protons, we get these, so a tri-substituted alkene forms. It forms faster, or if we lose this one, we have monosubstituted alkene that forms more slowly. So the thing is that removal of the proton leads to a transition state in which there is a monosubstituted double bond partially formed. A removal, so here it is. So here is the intermediate case when this mono-substituted double bond is partially formed. While the other proton, this one, if we remove that, this leads to a more stable transition state with the lower energy. And that's basically the explanation for both stereo and regio selectivity of E1 reactions based on the kinetic arguments. So which one forms faster, that will be some major product. But it's also true that E1 eliminations, or at least some of them, are reversible, and the alkenes may be protonated in acid to reform carbocations, and this reprotonation allows the more stable product to form preferentially under thermodynamic control. So that's once again kinetic versus thermodynamic product. Here is just a practical example, the E1 reaction in medicine. So that's a tamoxifen, important drug to fight against breast cancer, and that's one of the most common forms of cancer, and it works by blocking the action of the sex hormone estrogen. The tetrasubstituted double bond can be introduced by the E1 elimination, so and there is no ambiguity about where the double bond goes. Through the two stereoisomers form in about equal amounts. So here you see the E1 elimination reaction, and here you get tamoxifen and something, not sure if useful. So here is the OH group that was eliminated. So once again, protonated, and elimination forms this sort of double bond when the hydrogen from this carbon atom leaves. Good. E2 reactions. So these are second order bimolecular reactions. The E2 mechanism, just a reminder, base attacks at the same time when the leaving group leaves. So here is the example. We have some transition state when this double bond is partially formed, while this is partially destroyed, and after that a neutral alkene is produced when we create a double bond and the leaving group leaves. For this reaction, we should have correctly overlapping orbitals. So in the case of E1 reaction, we just have some leaving group that leaves, and that's it. Here we should collide two molecules, we should collide them properly. They should these orbitals should be basically on one line. So here is example of the correct stereochemistry and incorrect stereochemistry. So in E2 reactions, the product is dependent on the stereochemistry of the molecule. The leaving group and hydrogen must be anti to each other, meaning they must rest on opposite sides of the molecule. Since the deprotonation and the ionization are happening at the same time in this reaction, for there to be enough space, the two parts of the molecule must be as far away from each other as possible. So we are abstracting this proton from here, and these electrons will move here, and this bromine will will leave. And in this configuration, the process may proceed. In this configuration, it will not. So here we have these sort of reactions shown, and you might guess that this will influence the products that we get. Once again, an example. Let me close this. Okay, so we are waiting. So here we have two conformations with H and X coplanar, so syn periplanar conformation, and here we have the anti-periplanar or staggered, and in this case bonds are fully parallel, so we can abstract this proton and reaction will proceed. Where it leads us to. So here we have our reaction, our bromine is leaving, and here we have double bond formed. So you might guess that if we are abstracting some proton from here, it should be on the opposite side to the bromine. So these electrons will go here and create, this will be the major product. A pretty different case, it's when you have this CH3 group going here, and you have, let me draw it this way, you have a proton here, and you have your CH3 group here. We still can do something, but this will be pretty minor product. So that's what we have, and here is some leftovers if you abstract a different proton. So the same is true here. So once again, minor product, major product, and here you can see these gauche and anti-periplanar conformations, and guess what happens. So if we are abstracting some hydrogen, it should be on one line with the bromine, and of course we will have we will be more towards less hindered conformation. For example, these are two methyl groups and they don't want to be on the one side of the molecule, so that's why you have major product here and minor products in here. So good, that's what we have. Now let's check these examples. So here we have our molecule, and here's the reaction. So attack happens on these hydrogen atom. So these hydrogen atom will be attacked, electrons go here, leaving group leaves. That's what we have. Now let's check. Can we check this one or this one? Yes, something not working correct. Good. E2 eliminations can be stereo specific. Stereo selective reactions, they give one predominant product because the reaction pathway has a choice. So either a pathway of lower activation energy, some kinetic control, or more stable product, the thermodynamic control. Stereo specific reactions lead to the production of the single isomer as a direct result of the mechanism of the reaction. So stereo specific means you get one product. There is no choice. The reaction will not give you something different. And here we have the elimination reaction, and this is the result. So you cannot get something different like this phenol group on the other side. So that's only what we have. So alkene E, you cannot get Z. That's because only these proton can be attacked by the OH minus, by the base, and it should be on one line with the bromine atom. So this is the only configuration when this proton is on one line with the bromine, and that's basically what we get. So there is no other option. So this is a stereo specific elimination. Here is another case. Once again, hydrogen and bromine should be anti-periplanar. So that's the only hydrogen that can be attacked, and you see that this reaction leads to the alkene Z. So that's the case. The difference between these two reactions, we have different stereoisomers. So here this methyl group is coming towards us, so it's on one side with the bromine, and this methyl group is going into the plane of the page, so they are on different sides with the bromine group. So that's what we have. Good. One more example: elimination from the cyclohexanes. So here is the ring inversion. So you know there are two conformations for the cyclohexanes, and once again a hydrogen atom must be on one line with the living group, and only in this configuration we can attack that with the base and form our product. So E2 elimination will yield this sort of product. And for E2 elimination in cyclohexanes, both CH and CX must be axial. So you cannot get them parallel in the equatorial plane, so they will be not. They will be parallel only if they are axial, so only this case. And here is one more example of the reaction. I'm not sure if that works. Yeah, so we have some troubles here. I don't know. It started working. Whoa. So here is another reaction with Z alkene, and here you see this sort of reaction. Okay, and here is elimination from the cyclohexane. So here it is. Here you see the conformation, and only when hydrogen and bromine are in the axial position we can perform the E2 elimination. Here living group leaves, and we get a double bond here. Now we can do the same, but once again we need a suitable configuration when hydrogen atom and these bromine are basically on one line. And here we are eliminating that and creating a double bond. So good. Here are some more examples of the elimination. I will not get into that, but once again a reminder that everything depends on the conformation, and we want our molecular orbitals to be positioned appropriately. So we should have our bond to the hydrogen and to the chlorine. We want them to have them parallel, and that is possible only if they are in axial position. And you see that that in one of these cases, when we are performing this sort of elimination, here we have some additional group, this one, and this elimination is allowed only in these conformations. So the result we get, it will be locked in this position when the double bond is formed. And here is another example of the same kind. Once again, eliminating hydrogen, chlorine leaves, and once again it locks this sort of additional group in one position. So here's our here's our molecule, and let me check what do we have here. Here we have one conformation, but here is chlorine in the equatorial plane, so you cannot perform elimination. Here you have, no, this does not work, too bad. Here you have that chlorine in axial position, so now you can do that only with the hydrogen that is in axial position as well. Let's perform that. So here we have it. Now a double bond is formed. This double bond is trying to make here everything planar, so these bonds should be planar, and now these substituents are locked in certain position. Here is another example. Here we have it, and here's once again elimination, and substituents are locked in certain position. So here you see the results of these reaction. Okay, let's go further. These are elimination reactions of methyl chloride, so E2 conditions, strong base in 100% ethanol lead to 2-menthene through an anti-periplanar elimination, whereas E1 conditions, like dilute base in 80% aqueous ethanol, lead to a mixture of 2-menthene and 3-menthene. So different mechanisms may lead to different results of the reaction. So here are E2 conditions. So we can eliminate only these hydrogen, and only in the case when they are axial with the chlorine. So here's what you get, that's 2-menthene. Or we can get E1 conditions. These are conditions when the leaving group first leaves, so chlorine first leaves, so you can have different conformations at the moment when the hydrogen atom is abstracted. So any of these two atoms can be abstracted, so you get either double bond here or you get double bond here, depending on which hydrogen was abstracted. But that's E1. That's E1 because chlorine left. If this is E2, chlorine should leave at the moment we are removing proton, and basically that locks certain conformation. Here are some more examples, so I will not get into that. So here are examples of regioselectivity of E2 eliminations. Once again, everything is connected to the fact that we should have hydrogens and our leaving group in certain position. And of course, depending on the steric hindrance, we may have different results. So here is an example when hydrogens are sterically hindered, so we cannot get to the hydrogen, but we can get hydrogen off of the methyl group. So that may be the case as well. So everything depends on the situation. Good. So steric factors are evident in some of the E2 reactions, where changing the base from the ethoxide to tert-butoxide alters the major product from the more to less substituted alkene. So that's possible. So depending on what you have. So here is an example. We are eliminating the bromine. We get this double bond. And depending on the situation, we can either abstract these hydrogen atom, or we can abstract one of hydrogen atoms here in the methyl groups. And in case of sodium ethoxide, so this substance, we have more of this product, and in case of in the more hindered case, like tert-butoxide, you have more of these products. So it's easier for the large base to abstract some proton from here and create these double bond than to get to this product, because it's hindered with these CH3 groups. What else? Elimination regioselectivity. So E1 reactions, they give the more substituted alkene, and E2 reactions may give the more substituted alkene but become more regioselective for the less substituted alkene with more hindered bases. So look at the 3D geometry, and that will tell you something. Some rules like Hoffman and Zaitsev, so traditionally these are two opposite preferences for more or the less substituted alkenes, have been called Zaitsev's rule and Hoffman's rule respectively. You will see these names used along with a number of alternative spellings acceptable for Zaitsev, whose name is transliterated from Russian, but not for Hoffman. But there is a little point remembering which one is which. It's far more basically important to understand the reason why one thing is formed or another. I guess the last one type of the reactions, let me check that. Well, no, not the last one, but almost the last one type. These are E1CB reactions. So these are first order unimolecular reaction with conjugate base. I will not get into many details. So in contrast to the E1 reaction, which involves a carbocation intermediate, the E1CB reaction takes place through a carbanion intermediate. So we have negative charge here on the carbon atom, and base-induced abstraction of a proton in a slow rate limiting step gives an anion which expels a leaving group on the adjacent carbon. So here we have base. First, base abstracts proton. In previous reactions, we had either proton abstracted and leaving group leaving at the same time, or first the leaving group would leaving. Now we have proton abstraction first. This leads to the fact we have some more electrons here, so we get some carbanion. This is, in this case, that's resonance stabilized anion, so here it is. And then a leaving group at some point leaves. The reaction is particularly common in substrates that have a poor leaving group, such as OH, so two carbons removed from a carbonyl group. So the poor leaving group disfavors the alternative E1 and E2 possibilities, and the carbonyl group makes the adjacent hydrogen unusually acidic by resonance stabilization of the anion intermediate. So if this hydrogen is really willing to leave and this leaving group is a poor leaving group, you probably should expect something like this. Here's a simple example. I guess let's check this one. So here we have our proton abstracted, and this leads to the carbon anion that is stabilized with the resonance structure. So here you see some negative charge on the oxygen, and now the leaving group is trying to leave. Here it leaves, and this is a poor leaving group like OH minus, but in this case it was able to leave through the E1CB mechanism. Good. Here are some more examples. Once again, abstracting proton, stabilizing, and leaving group leaves. So nothing really complicated. Here are even more examples. So the leaving group is not lost from the starting molecule, but from the conjugate base on the of the starting molecule. So this sort of elimination, which starts with the deprotonation, is called E1CB. So CB for conjugate base. And once again, here you see a proton is abstracted. We have this sort of intermediate. That's a conjugate base, basically, because we have lost a proton, and now this is a rate determining step when our leaving group leaves. Here are some more examples of that, so you can check that. Later. Some even more examples. So I don't think we should get into all of that. Here is example with two phenyl rings helping to stabilize the anion and the carbamate anion at the leaving groups. Once again, we should have something that is able to stabilize negative charge, and here according to the Huckel's rule, we have a system, an aromatic system with these electrons. So we have fixed pi electrons, we have aromatic system, and it's pretty stable. So that's basically example of the stabilization. And here is one more example. You have a pretty acidic hydrogen atom, so it's happy to leave because you will get here an aromatic system that is stable more or less, and that basically helps you to perform E1CB elimination. The rate determining elimination step is unimolecular, so you might expect that you will have the first order rate equation. But in fact, this step is not the first step, so that's why you have some additional effects involved. So the rate is also dependent on the concentration of base, and that's because to get to that rate determining step, well, to that intermediate, you should create first that intermediate. So that's why you have base involved, because that base defines you how many intermediate you have, and only from that intermediate you proceed with the first order equation. But to calculate the concentration of that intermediate, you should use different equations that involve the concentration of base. So if you had your intermediate concentration known, that will be the first order equation, but basically we don't start with that. We cannot put that intermediate into flask. We are putting our initial substrates, initial chemicals, so we should use concentrations of that chemicals to define the overall equation, and that's why if we express the concentration of the intermediate through that initial chemicals, we get a little bit different equation. So here is the example of how do we derive that. So here is the equilibrium constant K that involves our base, and this base generates the intermediate, and then we have the rate constant K small that proceeds to our to our product. And you see that if we write the definition of the capital K, we can express the concentration of our intermediate that we basically need, and then we can use this concentration of our intermediate to express the the results. So for reactions with several steps in which the rate determining step is not the first one, the concentration of species involved in those earlier steps will appear in the rate equation, even though they take no part in the rate determining step itself. Well, because they determine the concentration of the chemicals that take part in that rate determining step. So that's a crucial thing to notice. Good. I guess I'll skip this one. Once again, just a small reminder, so as a recap. So E1, leaving group goes first and proton removal follows in the second step, so you go through the carbocation. E2, both events happen at the same time, proton removed, leaving group leaves the same step, and they should be properly aligned in the 3D space. And E1CB, proton removal in front, so you remove proton, you get carbanion, and then leaving group leaves. So here you have these sort of examples. So abstracting proton, getting carbanion, and then leaving group leaves, that E1CB, the E2 elimination, removal of the proton and leaving of the leaving group in one step, and E1 elimination, first leaving group goes away, you get carbocation, then you remove the proton. That's it. Once again, some notions. The regioselectivity, so the location of the double bond is defined by the position of the acidic proton and the leaving group. So where you have leaving group, where you have the most acidic proton, that will define you the regioselectivity of the reactions. E1CB may be stereoselective. This one, for example, gives mainly the E-alkene with D, but in proportion 2:1. The intermediate anion is planar, so the stereochemistry of the starting materials is irrelevant. The less sterically hindered, usually E product is preferred. So that's it, because the intermediate is planar. So here is a table where you have different reactions with different nucleophiles. So here you have some poor nucleophile, weakly basic nucleophile, strongly basic, or strongly basic but hindered nucleophile. And these are the types of reactions that these chemicals may undergo. So not getting through all the table, just some points. So methyl halides cannot eliminate, there is no appropriately placed protons. Increasing branching favors elimination over substitution, because you just cannot get to that carbon-atom to perform substitution. And strong basic hindered nucleophiles always eliminate unless there is no option. And good nucleophiles undergo substitution by the SN2 unless the substrate is tertiary, and then the intermediate cation can eliminate by E1 as well as substitute by SN1. So like you have very stable good intermediate. And one more point not shown in this table: high temperatures favor elimination by gearing up the importance of entropy in the free energy reaction. So this entropic term T delta S, that's the way, and this is a good way of ensuring E1 in ambiguous cases. So you just get your temperature higher. Here is an example of E1CB that we will probably meet in the future. That's a fatty acid synthesis, and that a typical example occurs during the biosynthesis of the fats when a 3-hydroxybutyryl thioester is dehydrated to the corresponding unsaturated crotonyl thioester, and the base in this reaction is a histidine amino acid in the enzyme, and loss of the OH group is assisted by simultaneous protonation. So here you have a base, abstracts a proton, you see the electrons flow, and you get this sort of intermediate. Now this oxygen gets protonated, you get nice living group like water, and double bond is reformed while other double bond is created in here. So here is the crotonyl ether, and here's your initial chemical. And the last one is just electrophilic addition, just getting really quickly through. So here we have some electrophilic attack of bromine on ethylene. So here you have ethylene, you have pi bond here, and these electrons in these pi bond, that they can be placed in the empty sigma star orbital of the bromine, and thus two bonds are created. So this is a bromonium ion. Pretty interesting case. And it's even a little bit hard to draw that with arrows. So you see arrows these are drawn this way, showing some non-bonding electron pair on the bromine involved, but anyway, that's what we have. I'm not getting into many details here, so just want to show you this sort of reaction. So creation of the bromonium ion, and then this bromine anion attacks once again on this ring, and ring opens, and here you have this sort of product. And here are the orbitals involved in the opening of the bromonium ion. So here you have the bromine attacks with electrons on these orbitals. So this is sigma star orbital, so sigma bond here, and this is anti-bonding thing, so sigma star. This is a normal SN2 substitution. The key orbitals involved are the HOMO of the bromide and the sigma star of one of the two carbon bromine bonds in the strained three-membered ring. So this ring is pretty strained because there are only 3 atoms. Here is example of the oxidation. So maybe, I'm not sure. Well, let me check. Let me check what we have here. Well, yes, maybe I will show you this example. I will show you this example and say maybe one word regarding Markovnikov rule, and that will be it. So here we have this sort of attack. So here you see what happens. So here we have an epoxide formed. So this is oxygen atom connected to 2 carbon atoms. Here we have a really strained ring, but that's how it works. So we have some here we have electron density. Let me show you in here to see all these orbitals. So here we have the pi bond. This is a field orbital, so it contains some electrons, and here we have electrophilic attack by a peroxy acid on the alkene. So these two oxygens, they are connected with sigma bond. So here is an anti-bonding orbital. It's empty. It's anti-bonding. It's empty in this case. So sigma star orbital. It attacks here. So these electrons will be placed onto this orbital, which means they will weaken the bond between two oxygens, because you have some electrons on the bonding orbital and anti-bonding. They are compensating each other, so this bond weakens, and now here 2 bonds are formed. So you get epoxide, and you get these bond broken, and that leads to creation of the double bond here. So here's more detailed scheme what happens. Once again, there are some troubles how to draw these arrows in case of this sort of attack, but anyway, if we forget for this part, just think in terms of orbitals, the rest is simple. So these electrons are going here, forming a double bond, this one, and these electrons are used to get this proton. And here is a transition state, so you see some bonds are partially formed, some are partially broken, and this is pretty complicated looking thing. And electrophilic addition to unsymmetrical alkenes is regioselective, so more stable cation leads to product. So once again, here we have it. If in this case we get some stabilized benzylic carbocation, here it's connected to the bromine. There are some more examples here, and this positive charge is much easier to stabilize than this charge, so you don't get reaction going this pathway, you get reaction going this pathway. And there is a traditional mnemonic called Markovnikov's rule for the electrophilic additions of the HX to alkenes, which can be stated as the hydrogen ends up attached to the carbon of the double bond that has more hydrogens to start with. Of course, I don't suggest you to learn these rules, so you may hear it referred to. As with all similar rules, it is much more important to understand the reason behind it. For example, you can now predict the product of this reaction, despite you cannot do that with Markovnikov's rule. So you have equal amount of hydrogen atoms for the both of these carbon atoms, but if you create a carbocation, so you get, let's say, charge plus here, when you remove something, you can stabilize, you can delocalize that charge into the ring, and you get much more stable carbocation than in case if you will have this positive charge here and there is nowhere to delocalize that, so you cannot or you cannot delocalize that so effectively as with this case. So that's why you can guess which will be your carbocation, and the place where you get this plus charge, your bromine will attach. So this will be the product, despite you cannot say with the Markovnikov's rule where to attach that bromine. Okay, and with that being said, I think that's everything I wanted to show you regarding the elimination reactions and all the other things.